Welcome students, welcome again to my new lecture. I am Mohammad Tanvir Ahmed, lecturer at Department of Civil Engineering, World University of Bangladesh. Hydrograph. It is the graphical representation of ditches with time, having ditches in y direction and time in x direction. So we can say the graphical representation of the ditches flowing in a river or stream at a given location with the passage of time is known as hydrograph. Here in this figure, we can say this is a hydrograph having ditches in y direction and time in x direction. This highest point is called peak point, and this decreasing curve is called recession limb. The hydrograph is of the following four types. First one is annual hydrograph, then monthly hydrograph, seasonal hydrograph, and last one is flat hydrograph. Usage of hydrograph. Hydrograph is used for the analysis of flood routing, flood forecasting, determining design ditches for any hydraulic structures, and flood damage mitigation. Here we can see this is a hydrograph with one peak flow. The hydrograph of this kind, which results due to an isolated storm, is typically single-peaked skew distribution of ditches and is known variously as storm hydrograph, flat hydrograph, or simply hydrograph. A flat hydrograph has three major parts, which are rising limb or concentration curve, crest segment, recession limb or depletion limb. In this hydrograph, from this point A to B, the curve rises, so this part or this portion is called rising limb or concentration curve. The part BC or the segment BC is called the crest segment, which is in between the 2 points of inflection with a peak P in between them. From this point C, the curve decreases, so the CD portion of the curve is called recession limb or depletion limb. This is the lag time TL, and the time interval from the center of mass of rainfall to the center of hydrograph is called lag time TL. This TB represents the time of surface runoff, and TPK is the time of peak from the starting of the rainfall. The flat hydrograph depends on various factors. The factors which affect the flat hydrograph can be categorized as physiographic factors and climatic factors. In physiographic factors, basin characteristics such as shape of the basin, size, slope, nature of the valley, etc. affect the flat hydrograph. In infiltration characteristics, land use and cover, soil type and geological conditions, lakes, swamps and other storage affect the flat hydrograph. And in channel characteristics, cross-section, roughness and storage capacity affects the flat hydrograph. And in the sides of climatic factors, storm characteristics, initial loss and evapotranspiration affects the flat hydrograph. The shape of the catchments depends on hydrograph. Here in figure, these are the shape of the catchment, and if the peak discharge occurs earlier, the shape of the catchments will be like this. If the peak of the hydrograph occurs later, then the shape of the catchments will be like this, and if there are two peak discharges, then the shape of the catchment will be like this. From the above discussion, we can say the hydrograph will have the following three components. These components are the rising limb, the crest segment, and the last one is the recession limb. Base flow separation. Base flow is the flow which is equivalent to infiltration and surface runoff occurs just above it. Here, this is a hydrograph, and we can separate base flow by drawing a straight line from the starting point of rainfall A to the same discharge level at point B. Simply we can say this A is the starting point of rising curve and this B is the ending point of a recession curve. If we draw a straight line joining these 2 points A and B, this is called the base flow separation by straight line method. That means the flow below this line AB is called the base flow or infiltration, and the flow above this line is called surface runoff. Straight line method. In straight line method, the base flow is achieved by joining with a straight line the beginning of the surface runoff to a point on the recession limb representing the end of the direct runoff. Again, we can use this formula to determine the number of days where the runoff will end. The formula is n equal to 0.83 into a to the power 0.2, where a equal to drainage area in kilometer square and n equal to number of days, where this n represents the end points of the straight line. That means n represents the point B of the straight lines. Unit hydrograph. A unit hydrograph is defined as the hydrograph of direct runoff resulting from 1 unit depth of rainfall excess occurring uniformly over the basin and at a uniform rate for a specified durations. Simply we can say a unit hydrograph is a discharge hydrograph resulting from 1 unit of net precipitation distributed uniformly over a watershed. Here we can see this is a unit hydrograph. That means this hydrograph has prepared by counting the depth as 1 centimeter, and this 6-hour unit hydrograph indicates that this hydrograph has prepared from a storm or rainfall that duration was 6 hours. There is an example. Let's read the question first. Given below are the coordinates of a 6-hour unit hydrograph for a catchment. Calculate the coordinates of the DRAs due to a rainfall excess of 3.5 cm occurring in 6 hours. So these are the coordinates of a 6-hour unit hydrograph, and using this data we have to calculate the DRAs, that means a direct runoff hydrograph due to a rainfall excess of 3.5 cm occurring in 6 hours. To solve this question, first we have to plot a discharge versus time graph, that means hydrograph, with the given data, and we will get a curve like this. And this higher curve we have obtained from the data of 3.5 cm rainfall excess, which we will calculate in the next page. So for this type of math we have to draw two hydrographs like this. The first one will be using the data given in question, and the second one will be using the data after getting the results. Here these two data, time and ordinate of 6-hour unit hydrograph, were given in question. We have to calculate ordinate of 3.5 cm DRAs, as this is the data of a unit hydrograph, and we know that unit hydrograph represents a hydrograph of 1 unit depth. So we can assume that this data is for 1 cm depth. And to calculate the DRAs of 3.5 cm, we need to multiply 3.5 with this data. For example, when the coordinate of 6-hour unit hydrograph is 25, and if we multiply this 25 with 3.5, we will get the coordinate of 3.5 cm DRAs as 87.5. Similarly, when the coordinate of 6-hour unit hydrograph is 50, and if we multiply this 50 with 3.5, we will get the value 175 for the coordinate of 3.5 cm DRAs. And when this coordinate is 0, and if we multiply this 0 with 3.5, we will get 0 as the coordinate of 3.5 cm DRAs. Similarly, we have calculated all these values by multiplying these values with 3.5, and after calculation of this ordinate of 3.5 centimeter DRAs, we have to plot a hydrograph using this data, and we have showed this hydrograph in the previous slide, and the highest graph or the highest curve represents the ordinate of 3.5 centimeter. Application of unit hydrograph. Using the basic principles of the unit hydrograph, one can easily calculate the DRAs in a catchment due to a given storm if an appropriate unit hydrograph is available. So that is the end of our today's lecture. Thank you everyone.